Hello, everyone. So we will continue our session. Our first speaker is Vasyl Ustimenko, who will talk about on geometries of Kac-Moody groups and symbolic computations. Please, Vasyl.
Thank you, Kaveh, for the announcement of my talk. I remember well late Vladimir Vasilievich Sharko, who was prominent member of our community, algebraists in Kiev, and your teacher. In fact, my teacher, Lev Arkadievich Kaluzhnin, and Jacques Titz were students, former students of famous Emil Artin, and they keep letter exchange continuously, regularly. So it had impact on my PhD thesis, on topic of this thesis. It was dedicated to actions of Weyl groups and BN pairs on the elements of their geometries. So I'm glad to return to this topic today. And I will start with some definition. By the way, I just have to say that I am presenting here Royal Holloway, University of London, where I am a research fellow, and Institute of Telecommunication of National Academy of Science of Ukraine, where I'm working as head of Department of Cybersecurity. So I will start with definitions and will show how it could be applied to problems of algebraic geometry and its computational aspects. So first I will start with generalization of geometries of Chevalier group. As you know, the incidence system is a triple gamma IT, where I is a symmetric antireflexive relation, simple graph. On the vertex set gamma, T is a function from gamma to n, set of types. This is type function on the set n, such that alpha incident to beta and T alpha and T beta coincide. That implies that alpha equals beta. This is David Hilbert approach to geometry. So from this point of view, classical geometry or geometries of simple groups over finite fields or other fields are incidence systems. So in case of two types, we usually talking about incidence structure like projective plane. An important example of the incidence system as above is a so-called group incidence system, gamma GGS. S belongs to capital S. Here G is the abstract group, and GS is the family of distinct subgroups of G. So elements of gamma GGS, incidence structure, they are left cosets of GS in G for all possible S from S. Cosets alpha and beta, say left cosets, are incident precisely when the intersection of alpha and beta is not empty set. The type function is defined T alpha is S, where alpha is left coset GGS for some S belonging to S. So, example, let WS be a Coxeter system, i.e. W is a group with a set of distinguished generators, S1, S2, SL, and generic relations of kind SI, SJ, MIJ. So here MII equals 1, so SI are involution. And this is symmetrical L time L matrix with of diagonal elements such that MIG bigger or equal than 2. So, of course, a group can be finite or infinite. So we can take a so-called standard subgroup of Weyl group, take generators S and subtract just single element Si, and the so-called standard subgroups of Weyl group, and consider a group incidence system gamma W, which is just totality of left cosets of W but Vi with standard incidence relation defined above. So Vi recall that they are known as maximal standard subgroups of W. Now, geometry of B pair. So this is famous definition by Jack Tietz. Maybe because of that definition, he got Abel Prize in 2008 together with John Thompson. So let G be a group, be a group, B and N subgroups of G, and S be a collection of cosets of B intersect N in N. We call GBNS Tietz system, or we say G has a Bn pair. If G is generated by Bn, intersection B and N is normal in N. S is set of involution where which generate W. This is normal factor group of N over B intersect N. Now, requirement 3, this set SBW, it must be inside of the intersection of double cosets BUB and BSWB for any S from S as generator and W from the group W. And last, the condition SBS for each S differs from B. So these properties I4 imply that WS is a Coxeter system. So W is a Coxeter group. And in fact, the group G, for instance, if it's a finite group, then it's supposed to be simple or quasi-simple. So it has some normal, large normal subgroup, which is a simple group. So just for example, if we take GLN over F, general linear group, as G, B as group triangular matrices, and N is group of monomial matrices, we will get projective geometry. That's nice definition. You see that it in terms of abstract group theory, no fields or rings are visible here. So now the geometry with each this Bn pair or Tietz system, we can associate the geometry, defines subgroups Pi in the form BWIB, Wi well already defined. They call standard maximal parabolic subgroups of G. They are really maximal subgroup here. And we can consider group incidence system gamma G just as totality of left coset Pi in G. And it's commonly referred to as Lie geometry of G because of many examples of real Bn pairs are connected with Lie geometries. Now, one of the example of group with Bn pair is Kac-Moody group, which defined via pair A, F, where F is field, and A is generalized Cartan matrix. So this is just general square matrix with diagonal entries 2, negative integers in other entries, just zeros have to be located symmetrically with respect to main diagonal of the matrix. So, in fact, such a square matrix, generalized Cartan matrix, defines so-called Coxeter-Dinking diagram, and reflection groups by this Cartan, generalized Cartan algebra. I just skip this definition. You can find it. It's in Bourbaki. So how the group G is defined? First step, we need to define Kac-Moody algebra, LEF. So in terms of relation and generators, defined by this matrix A. And after take inner automorphism of this Lie algebra, and they form the group with a Bn pair, and it has a Tit system GBNS. So generalized Cartan matrix defined the Weyl group WA of the Bn pair A. So if VA is finite reducible Coxeter group, then G is a Chevalier group over the field F with associated Coxeter-Dinking diagram XL, which belongs to the list AN, BN, CN, DN, G2, F4, E6, E7, E8. So let's fix Kac-Moody group GF, XLF with corresponding Weyl group W. So because it has Bn pairs, there is a geometry of this group. We have maximal parabolic subgroups, and taking this group incidence system. So let's describe this geometry in as algebraic variety in sense of the Zariski topology. So the following bipartite graphs are analog of planar ternary rings introduced by Marshall Hall for the description of projective planes. So let K be a commutative ring with the unity. Jordan-Gauss graph K is an incident structure with partitions at P points and L lines, isomorphic to affine spaces V1 and V2, not just free modulus over the commutative ring K. So, and incidence relation is given by special quadratic equation over the commutative ring K, such that the neighbor of each vertex is defined by the system of linear equation given already in its row echelon form. So we assume that Vi are finite dimensional spaces or just spaces of kind Kn in finite dimensional case. Let's look at alternative definition which gives the structure of this group. So Jordan-Gauss graph GK is a special graph of type bipartite graph of type SR. So we are taking two integers, positive integer S and R, bigger or equal than 1, given by the following way. We identify points and lines as tuples, points x1, x2, xn, etc. And they form a affine space. And lines are tuples of y1, y2, yn. So here brackets and parentheses allow us to distinguish point from line. If x and y are incident, then the following relation hold. So first, recall that we have special parameter S and R, And the first equation looks like this. A1 xs plus 1 minus b1 yr plus 1 equals f1 x1 x2 xs y1 y2 ys. F1 is polynomial multivariate expression. Here the list of variable coefficients are taken from the k. So next equation, we just add some variable xs plus 1 and another variable yr plus 1 to the list, not xs plus 1 twice, that's a mistake. And it looks like this. And we continue to add variables, and intermediate equation looks like xs plus m minus bm yr plus m equals fm x1 x2 xs plus 1 x plus m minus 1, here m, and y1 y2 yr plus 1 etc. yr plus m minus 1. So here these parameters ai, bi are supposed to be not zero divisors, so regular elements of the ring. And if fi are quadratic multivariate polynomials, so this is really if we specialize x1, x2, xs as some parameters p1, p2, ps plus 1, and etc., then the neighbor of point will be given by linear equation, because here we will have linear forms after the specialization, and it's already in row echelon forms. So we say that we refer to these graphs as Jordan-Gauss graph. We say that two Jordan-Gauss graphs, G1 and G2, over possibly different rings, are symbolically equivalent if they are given by this system of equation of this kind one, with the same number of equations, same parameters n, r, and s, and a quadratic polynomial fi have the same list of monomial terms. Well, we are taking terms with non-zero coefficients, so it must be the same list. We can call that this list is symbolic type of polynomial expression fi. Now, let gamma be an incident system with the partition sets gamma I equal 1 to m, and incident relation I. We say that partition of gamma into set gk, k equal 1 to n, etc. L, is Jordan-Gauss equivalence over commutative ring K if for incidence element alpha and beta from this incidence system, there is a Jordan-Gauss graph gk alpha, gk beta over K with the set of points gk alpha, one of this set, and gk beta, another set, such that induced graph of gamma restricted on gk alpha and gkb is Jordan-Gauss graph. So this Jordan-Gauss graph gk alpha k beta. And first theorem, let F be a field and GF be a Kac-Moody group, and gamma GF be a Kac-Moody geometry of GF. Then there is Jordan-Gauss partition of gamma GF defined by over F. So we can look at Kac-Moody geometry as kind of disjoint union of these bipartite Jordan-Gauss graphs. Now, what about this partition? Let the Kac-Moody group fixed, we take B plus and B minus, it's Borel subgroup. So B plus generated by unipotent subgroups corresponding positive roots, and B minus are generated by root subgroups corresponding negative roots. So B plus and B minus are, of course, isomorphic. So we take maximal parabolic subgroups Pi as such that they are containing B plus. B plus will be group B in our Bn pair, and we can take the corresponding geometry and consider the orbits of B minus on the set of elements of this geometry. So we will get this Jordan-Gauss partition of this Kac-Moody group. And just useful proposition that orbits of B minus, so classes of this Jordan-Gauss equivalence relation, are in one-to-one with elements of Weyl geometry of this group. So, and we can consider the map R, which give the element alpha corresponding partition, class equivalence, and this class equivalence corresponds to Weyl geometry, so we get homomorphism this way from geometry of Bn pair to the geometry of Weyl geometry of this group. Now definition. What we are going to do. This object is well-defined gamma GF over the finite field, and I would like to define the analog of this object over commutative ring with unity. So what we are doing? Let's fix the Kac-Moody group with Coxeter-Dinking diagram XL, and take this partition described in proposition 1 on classes GS. Now let's take some non-trivial induced graph Jordan-Gauss GS S prime, define over the field F, because we have equations defined over F. And what we will do, we can take these equations of this graph GSS prime, so I will come back to the equations. And here we have coefficients of F1, F2, Fm, which are from the field. And we just take them out and replace them by elements from the ring. So factually, we each Jordan-Gauss graphs of Kac-Moody geometry, instead of this graph, we taking symbolically equivalent to this graph, but defined over the commutative ring K. Of course, it must have unity, because we need requirements that these parameters A1, B1, A2, B2, AM, BM are zero divisors, so we need some non-trivial maybe, or trivial maybe, multiplicative group for this K. Now, let's go further. And now, actually, this definition is interesting even in the case of field, without change of field f, because if we take some Kac-Moody geometry, that coefficients of these Jordan-Gauss graphs defined in terms of generalized Chevalier basis of correspondingly algebra. They are integers if we have field of characteristic 0. And we are just taking this coefficient, and instead of them, we replace them by randomly selected elements from the ring. So that's and of course to have this object, this new incident system over the ring, we need to collect a lot of data. So we need to keep somewhere all coefficients of f1, f2, fm, which we select. So this is the symbolic data, so-called data, and we can denote this incident system as gamma indexed upper index D. This is data of coefficients. XL, this is Dynkin-Coxeter diagram, and K is the corresponding selected ring. So why this is important? Because we can apply this Jordan-Gauss geometries of this kind derivated from Kac-Moody groups with correspondingly to selected commutative ring, and consider some application in computational algebraic geometry. So I will present some result. Let's consider the affine Cremona semigroup CS and K. So K here is a commutative ring. We are taking multivariate ring K x1, x2, xn, where x1, x2, xn are list of variables, and consider all endomorphism of this ring. Okay, such endomorphism f can be given by its value on generic variables x1, x2, xn. So we have f x1 is f1 multivariate polynomial, f x2 is f2, f xn is fn. So each f induced the map f prime, which sends x1 to f1, x1, x2, xn, x2 to f1, x1, x2, xn, xn to fn, x1, x2, xn of the affine space Kn. So this is multivariate transformation of affine space Kn. It's possible to prove that this induced map f, the kernel of mapping f to f prime is trivial if K has characteristic 0, but in general case it could be some non-trivial kernel. So we may assume that all polynomials f1, f2, here f2 must be, fn are given in their standard forms via the list of their monomial terms ordered lexicographically. And we can define degree of the map as maximal value of degree of this polynomial fi. The density dense fi x1, x2, xn is its number of monomial terms. So we have degree and density of f here, and we can use the incidence structure that I presented of kind gamma dxl. Here I select special form for the ring K. This is multivariate ring K x1, x2, xn, which of course infinite one. Then in case of simplest case, xl equal al, and get the following result of computational algebraic geometry. Let K be commutative ring with unity. For each positive integer n, and integers n and d at least 2, and s bigger or equal 0, there is a non-commutative subgroup H of affine Cremona semigroup CSN K of all endomorphism of K x1, x2, xn such that maximal degree of representative of H is D, and the density of elements from H are of size ns. So we can form a subgroup of affine Cremona semigroup with elements of prescribed degree and density. So, of course, we can consider subsemigroup H prime, which is larger than H, which consists of elements of prescribed degree and density. But what here is important, this is a kind of non-trivial result, because if we take two elements of a affine Cremona group of degree T and S, then in general position, like with random coefficient, then the composition of two maps will have degree Ts. So degrees are growing. So the fact that degree of elements of this subgroup H are bounded by D is far from trivial, and this property ensures that we can compute the composition of two maps from H in polynomial time. Because without this, this can be very difficult problem. And we need even to compute n composition of n randomly chosen elements of H and compute the composition. So that is the first application. So that maybe I go to the next task. So assume that we have multivariate map F, which is bijective on Kn. Okay. Then the trapdoor accelerator T of F is a piece of information such that knowledge of T allow us to compute the re-image of F in polynomial time. We say that T is computational accelerator of speed alpha if its knowledge allows to compute the re-image of F and its value on given elements of time or n alpha. So what we have here, if we have multivariate map F given by system of polynomials, then computation of re-image, it's NP-hard task, and even more, it has sub-exponential complexity, because you know that, for instance, the method of usage of Gröbner basis is very nice, looking nicely, but it has computational complexity, which is sub-exponential. So sub-exponential. So the same complexity with old Gauss elimination method. So next result, theorem. For each parameters n d bigger than 2 and alpha less than d, there is an bijective polynomial map f of Kn onto Kn on degree d, density of size O large and alpha, with the computational accelerator of speed O n. So we can design the maps with some magic piece of information T, which allows to compute reimage. So these two statements, theorem 2 and theorem 3, are very important results of algebraic, of multivariate cryptography. Because this platform of group H can be used for protocols of non-commutative cryptography, which are generalization of Diffie-Hellman protocol. And next theorem, which I hear about this trapdoor accelerator, theorem 3, allow to construct public keys. So we have two users. One user have only public rule, the map F given by standard form of this Fi, but another one has F together with this magic trapdoor accelerator. So one person can only encrypt, use this F to the tuple of data, but another can decrypt. So that's some my publications in European Journal Mathematics here. And I skip theorem 3 because I just would like to demonstrate the computational the idea how to use geometries for construction of such map or such subgroups. So let's consider the incidence gamma dxl x prime. We can take some Jordan-Gauss graph and consider the elements, the walks. Take the ring K prime, which is Kx1, x2, xn. Take the path in this geometry starting with the tuple, special tuple x1, x2, xn, this x, and here a1, a2, an. Then the destination point, the last one, maybe again belong to the same Jordan-Gauss graph. And suppose it has coordinates g1, g2, gl, we can take the map x1, x2, xl to g1, g2, gn, multivariate map generated by the walk in this geometry. So this way we design this special multivariate transformation. So thank you very much for your attention. So my time is almost finished, and maybe nice to have extra time for questions. Thank you.
Thank you very much. Thank you very much indeed for a very insightful talk.